discuss liquids and solids. A lot of this chapter is going to cover the concept of intermolecular forces, the forces in between one molecule and another molecule. We're going to cover 9.1, 9.2, skip a bunch of stuff in our solids, go on to 9.8, 9.9, and 9.10. So we're going to look at intermolecular forces first, and then talk about a summary of those forces, look at change of state, and look at different phase diagrams. So some questions to consider. Why is white phosphorus stored in water and not left out in the open like sulfur? So they're both in the same column in the periodic table. They should behave chemically in a very similar sort of way. Why do we keep one underwater, and why do we keep the one exposed to air? What causes the steaming on a piece of dry ice? White phosphorus is actually really, really nasty stuff. That's what the picture is on the left. That is used as flares, but it's also considered a war crime if you use that on people. So first we're going to look at intermolecular bonding. So atoms form molecules by sharing electrons. That's what we looked at in Chem 122. And if you had Chem 122 with me before, I said Chem 122 was all about the electrons. That's how we made our link between one atom and another atom. That's how we have polar bonds and non-polar bonds, and the degree of sharing that goes on between those. And those polar bonds could make polar molecules. Right, so atoms form molecules by sharing electrons. That's bonding within the molecule. And those are generally going to be stronger than intermolecular forces. Those are when you're looking at the energy between one molecule and another molecule. So if you think about people, right, there are forces that are holding your body together. Right? And so molecules are kind of selfish. They're thinking like, okay, well, I'm going to keep myself together, and my interaction with somebody else, another molecule, is not going to be as strong. Liquids and solids are the condensed state of matter. Remember, we're going to cover three states of matter in Gen Chem. We've got solids, we've got liquids, and we've got gases. And they're going to be formed. Which state you're going to be in is going to be determined by what your temperature is and the strength of those forces of attraction between one molecule and another. So they're formed by forces that may involve covalent bonding, ionic bonding, and mostly intermolecular forces. So in our three states of matter, we've got a gas where molecules are spread out, they're fast moving. We can treat a gas as being mostly empty space with no real contact between molecules. That's one of our assumptions from the ideal gas law. In a liquid, this is our first condensed state of matter. A liquid is free to form the shape of its container, but the volume is conserved. In a gas, it will expand to fill the entire container and still be conformal. So in a liquid, our volume is fixed, but it's free to move around. The molecules are close to each other, but they're sliding past one another. In a solid, they're all arranged nice and tight to each other. They're going to have a fixed volume and a fixed shape. We undergo phase changes. Those are change of states from one to another. So a state from a solid to a liquid to a gas doesn't involve any change in the molecules themselves, but it does involve a change in the energy among the molecules. And you'll notice a couple of these things where I've gone through and I fixed what the stock slide is saying to reflect something that's a little bit more accurate of what's actually happening. So if we're going from a solid to a liquid, by adding energy, the motion of the molecules is going to increase. The molecules are going to have greater movement, and the disorder is characteristic of a liquid. So those things are not in a fixed position. One atom or one molecule is free to move around and change its location. In going from a liquid to a gas, you're going to add even more energy. And by adding more energy, the individual molecules can move further apart from each other, reducing the interaction between one molecule and another. Okay. And so when we talk about temperature, we just remember that thermometers are just speedometers for atoms. Right? So the faster you're moving, right, we've got an equation that says Ke is equal to 1/2 mv squared. As you increase your temperature, you're increasing the motion of those molecules, you're increasing their kinetic energy. We've got a couple of different types of intermolecular forces. So these are very important. You want to characterize these, write these down, get out your notebook, and make a list of these because these are going to come up throughout this chapter. All right, so intermolecular forces are the ones that are coming between molecules. And there's really 5 basic ones that we're going to cover. First is ion-ion. That's when you've got 2 ions, like sodium chloride, NaCl. You've got Na, which is a plus, and Cl, which is a minus, right? And you're looking at the interaction between 2 ions with full charges or multiples of full charges. We have ion dipole, in which the interaction is between an ion with a full charge and a polar molecule, so like between water over here on the right and sodium on the left. We have dipole forces that are dipole-dipole interactions, so between 2 polar molecules. The most famous example of that is hydrogen bonding, and we'll talk about that later. So here we've got bonding within the intermolecular forces within liquid water are going to be mostly hydrogen bonding interactions. You can have dipole-induced dipole. So if you have a polar molecule like water on the left and something like a straight chain alkane on the right, which is a nonpolar molecule, as the polar end of the molecule with the dipole approaches that nonpolar molecule, it's going to distort that electric field. It's going to push those electrons out of the way and shift them. And now I've got an uneven distribution of electrical charge. I've got a little teeny tiny dipole that's developed in this nonpolar molecule. And so my nonpolar molecule becomes a little bit polarized. And last, you've got London dispersion forces, which are very similar to the dipole-induced dipole, except now we've got 2 nonpolar molecules that come close to each other. Their electric fields repel each other, and when we do that, we've distorted their electric fields around the molecules and induced a little bit of a dipole. Dipole-dipole forces are going to be exhibited by polar molecules, right? Because you can have molecules with polar bonds that are not polar molecules, like CO2, that behave in an electric field. They're going to attract each other electrostatically, so there's a partial positive end on one molecule and a partial negative end on the other molecule, and opposites are going to attract. This is also called dipole-dipole attraction. Dipoles are going to find the best compromise between attraction and repulsion. In other words, they're going to find the state that's going to minimize their potential energy. They're going to find the lowest energy position. Because molecules, like people who do chemistry, we are all lazy, right? We want to do it the easy way. We want to find the lowest energy way to do things. Right? So some characteristics. These are only going to be about 1% as strong as covalent or ionic bonds. So they're a lot weaker than the electron bonds that are holding the molecules themselves together. The forces are going to grow weaker as the distance between the dipoles are going to increase. And why is that? To stop and think, what do you know about how those electrostatic forces work? Right? So this is just going to be a throwback to Coulomb's law, which we covered in Gen Chem 1, but as you move those charges further apart, right, you've got your magnitude of your charges, and it's going to scale with the square of the distance. It's one of those inverse square laws like photon intensity. And if you think about like holding a magnet up to a refrigerator, right, nothing, and then as you get close, that force gets stronger and stronger and stronger. So same sort of thing happens with our electric attractions. So our dipole-dipole forces, this is a schematic for that. It's the electrostatic interaction between 2 polar molecules. So I've got a plus end on one molecule and a minus end on the other molecule over here. And if we take this, we take a bunch of those, right? It's going to move those things around in such a way that our forces of attraction are going to be maximized and our forces of repulsion are going to be minimized. And so our plus and minus charges will attract each other, but our plus charges will repel each other, and our minus charges will repel each other. And things are going to move around until they reach a state that's going to minimize those forces of repulsion and maximize those forces of attraction. Hydrogen bonding is our very special case of a dipole-dipole interaction. Hydrogen bonding is going to come up in lots and lots of places. So if something is acting weird, right, how do things work? Well, the default answer is going to be hydrogen bonding, right? So that could be one of your go-to answers, like, why is this doing this? Hydrogen bonding, right? Why does water have such a really high boiling point compared to other molecules of its size, right? So methane is a gas at room temperature. Ammonia is a gas at room temperature. Why is water a liquid at room temperature? Hydrogen bonding. How does DNA work? Hydrogen bonding, that base pair interaction between one base pair and another base pair, that's a hydrogen bonding interaction. Right? So hydrogen bonding is really, really important to us as a species and for us as things that are alive. So it's a very, very strong dipole-dipole force that can be noticed when hydrogen is bound to one of three highly electronegative atoms. It can be nitrogen, oxygen, or fluorine. And it's going to have a lone pair of electrons. So you're not always going to see hydrogen bonding just because you've got a nitrogen with a hydrogen stuck on it. It's got to have that lone pair of electrons. And it's really only going to happen with nitrogen, oxygen, and fluorine. I can't think of any examples that have any of those off the top of my head that are an exception. So nitrogen, oxygen, and fluorine. The strength of these interactions are characterized by the polarity of the bond, how close the dipoles are to each other, and the size of that hydrogen atom being so very, very tiny, right? And so that hydrogen atom is packing a lot of plus charge into a very, very small package. And we said fluorine, remember, acts weird because it's taking a lot of negative charge and putting it into a very, very small package. And again, that all goes back to Coulomb's law, where you're looking at, well, what's the distance between two charges? And if you're fluorine or if you're hydrogen and you're really, really small, well, your internuclear separation is going to be small, which means you're going to be close to something else. Such bonding affects physical properties of elements, and it is hugely important in organic molecules, such as DNA. A lot of protein folding is going to depend on hydrogen bonding. A lot of enzyme mechanisms are going to depend on the shape of that enzymatic pocket and how whatever the substrate is going to fit in there. And oftentimes that's going to be controlled by hydrogen bonding. So hydrogen bonding among water molecules, this is what water kind of looks like on the molecular level. You've got an oxygen, and it is nominally bound to two different hydrogens. So here's a hydrogen on the left and hydrogen on the right. But for this hydrogen's perspective, right, what's the real difference between this oxygen, which has a lone pair of electrons sticking out here, and this oxygen to which it is bonded? Right, so this guy is kind of a little loosey-goosey hydrogen, right? It can go over here and spend time over at the neighbor's house and be like, I don't know what's going on. We'll hang out with this hydrogen, with this oxygen over here. And like, oh no, this is my hydrogen, right? It's like those people who think they own a cat and really that cat is going to three different houses, right? That's what that hydrogen can do. Right? And so there is a very strong attraction between this hydrogen and the lone pair of electrons in this highly electronegative oxygen over here, which means that there's going to be a strong force of attraction between here and here, almost as strong as the interaction between this hydrogen that is bonded to this oxygen. And so sometimes some of these hydrogens might just move from one oxygen to another. We call those labile hydrogens. That's part of how acids and bases are going to work. And we're going to see that coming up in a later chapter. So those blue dotted lines represent the hydrogen bonds between the water molecules, and those are the intermolecular forces that are going to occur in water. It's all going to be hydrogen bonding. Again, that's why water is weird. We will see that is why snowflakes form beautiful six-sided crystals. It's because of this hydrogen bonding that happens. London dispersion forces are also known as van der Waals interactions. You may remember van der Waals from the van der Waals correction to the ideal gas law. These are going to exist among all molecules, including noble gas atoms and nonpolar molecules. So this is everywhere, but it's going to be the weakest of our forces, right? So our ion, they're going to be really strong, but you got to have an ion. Our dipole are going to be pretty strong. It's going to be a little weaker than ion, but you got to have something that's got a dipole. Right? Our dipole-induced dipole, you got to have something with a dipole and something that's nonpolar. So we're getting weaker and weaker and weaker as we go along, but we're getting more and more molecules included in that mix. Right? So all molecules are going to interact with each other, right? Even noble gases, right? Helium atom is going to walk along and it's going to bump into another helium atom. There's going to be some interaction. Right? We have an instantaneous dipole that occurs accidentally in a given atom or nonpolar molecule, and it's going to induce a similar dipole in a neighboring atom or molecule. It's going to instigate a weak and very short-lived interatomic or intermolecular attraction. So those guys, electric fields repel each other, right? One molecule comes close to another one, those electric fields are going to repel each other. You're going to induce a little bit of polarity. Now you got some very tiny transient short-lived dipoles. They're going to have attractions and repulsions. So we have this term called polarizability that is going to describe the strength of those van der Waals or those London dispersion forces. It's the ease at which the electron cloud of an atom can be distorted to produce that dipole charge distribution. So some molecules are small and hard and dense. It's really hard to move their electrons around. Right? Some molecules are big, fluffy molecules, and it's easy to push their electrons around. So the size and shape and how strong those electrons are bound to that atom or molecule are going to matter. So something like helium, right, is going to be small and round, and it's going to have smaller van der Waals forces or smaller London forces because it's got a lower polarizability. It's harder to move those around. Right? Something that's bigger, like argon or xenon, it's also a noble gas, is going to be even easier because of its size and how loosely bound those outermost electrons are. And again, this is what? It's just that Coulomb's law again. Oh, it's bigger, and so it's got less force of attraction because its internuclear distance is greater, right? So it's going to be easier to move those around. Right? It's going to be even easier if something is a football shape. Right? So if you're more of a rugby ball shape, you're a linear molecule, like a straight chain alkane, like if you're butane, right? Or if you're propane, and you're a series of chains of molecules, and you're not linear anymore, well, it's going to be easier for you to push things on this end and kind of smoosh them over that way. Some molecules are going to be even easier. The bigger you are, going to be loosely bound, right? So something big and globular, like, like a fullerene, right? It's going to be non-polar, but really big. Right? It's going to be easy to push those electrons around, very easy to induce a dipole. And so it's going to have a relatively strong London dispersion force. Right? So this is kind of a graphical representation of that from your book. Each of those little dots represents the probability of finding an electron in a given space at a given time. So we've got atom A on the left and atom B on the right. And as they get closer to each other, you'll notice that there is less density over here on the right side of atom A and more electron density on the left side of atom A. And so we've got a partial negative charge on the left side of A, a partial positive charge on the right side of atom B. Same thing is going to happen to atom B. Right? It's going to be less density over here. Right? It's going to induce this dipole. That's going to kind of push these molecules or push those electrons around. And so this guy is going to see this plus charge. Some of those electrons that were around atom B are going to be like, oh, hey, I'll be attracted to this partial positive charge. And so some of that electron density on B will shift over a little bit. Right? And it's going to leave this empty space over here. So you can induce this dipole. Now, this doesn't last for very long. right? Because the chances of you kind of asymmetrically populating your electrons is pretty low, but it does happen. And when it does, it can induce this similar uneven distribution or polarization in the other atom next to it. Right? So let's do a quick concept check. Which of the following is going to be the strongest bond? Is it going to be an intramolecular bond, B, an intermolecular bond, or C, James bond? Okay. Now, I want you to be able to justify your answer with a valid reason. Why is it that you that you should have picked A, right? The intermolecular bond, whatever your covalent bond is, whether it's ionic or covalent or right, whatever your thing is that's holding your molecule together, your actual electronic bond, that's going to be strongest, right? Even better, use a table. Back that claim up with numbers. That's what makes us scientists, right? We're going to make some observations, we'll put a number on it, right? So you can find a table of bond strengths, right? You would have done that at the end of Gen Chem 2 when you were looking at, well, here we got my bond dissociation energies, right? How much energy is going to be informed in the created in the formation of oxygen from its basic, or CO2 from the basic elements, oxygen and carbon, right? And then you've got tables of intermolecular bonds, right? So look at the numbers. Or is one going to be in kilojoules and one in joules, for example? Right? So justify those things with a number. Although, honestly, can you beat James Bond? I don't know. Right. So let's identify the molecule that is capable of forming stronger intermolecular forces. Is it going to be A, nitrogen, or is it going to be B, H2O? So pause, give yourself a moment or two to think. Okay, now let's justify our selection with reasoning. Right? So nitrogen, right? As a molecule, nitrogen is going to be nonpolar. Right? So the intermolecular forces that are going to dominate in nitrogen are just going to be the van der Waals or London dispersion forces. What about water, H2O? Well, we know water is a polar molecule, so it's going to have dipole interactions. But not only that, it's got this hydrogen bonded to an oxygen, and there's a lone pair of electrons out there on that oxygen, which means it can undergo hydrogen bonding as well. Okay. Let's look at these guys. We've got some Lewis structures. We've got ethanol and dimethyl ether. Right? These are structural isomers of each other. They've got the same atoms, but they've got different arrangements of those atoms, and so they're going to behave chemically differently. Structure defines function in chemistry quite a lot. So over here, we've got ethanol on the left, and over here we've got dimethyl ether. Right? Which one of these two do you think is going to have a higher boiling point? Okay. Well, to do that, we're going to think about what are our intermolecular forces. For us to do boiling, we need to overcome the forces of attractions between molecules. We need to overcome those intermolecular forces to go from a liquid phase to a gas phase. So the higher boiling point is going to be the one with the strongest intermolecular forces. Now, if I look at this dimethyl ether over here, this is going to be a polar molecule, right? Because these two sets of lone pairs are going to bend this molecule, so it's not going to be symmetric along that one axis, so it'll have a little bit of a dipole. So it's going to be able to undergo dipole-dipole interactions. Our ethanol over here, right, has a hydrogen next to an oxygen with lone pair of electrons, which means it can not only be polar, it's going to undergo hydrogen bonding, and hydrogen bonding beats regular dipole-dipole interactions. So the boiling point of the ethanol is going to be higher, which means that ethanol is going to be a liquid at room temperature, and it's going to boil off later or at a higher temperature than the dimethyl ether. Okay. So which gas would you expect to behave more ideally at the same pressure and temperature? Would it be carbon monoxide or nitrogen. Right? So we're going to justify our choice with a valid reason. Which one is it going to be? Okay. You should have picked nitrogen, right? Because nitrogen is going to be a nonpolar molecule. Right? Carbon monoxide is going to have a partial positive on the carbon and a partial negative on the oxygen, which means it's going to be able to undergo dipole-dipole interactions, which means it's going to have stronger forces of attraction, which means it's going to deviate from the ideal gas law. Remember, you may remember some of the assumptions inherent in the ideal gas law, especially the no interactions between molecules. Well, if I've got something with a dipole in it, well, this partial positive on one carbon monoxide molecule is going to be attracted to the partial negative and of another carbon monoxide molecule, whereas poor old nitrogen over here only has London dispersion forces. All right, section 9.2, the lipid